Hello everyone, thank you so much for coming. So I'm going to be presenting my PhD research titled Trajectory Planning for Flights in Multi-Agent and Dynamic Environments. So over the past few years, we have seen some real-world applications for autonomous UAVs, like package delivery between different hospitals, light shows, space exploration, and also videography. The thing is that the algorithms running behind all these videos rely on at least one of these three assumptions. Some of them assume that the environment is either static or at least quasi-static. Then there are other algorithms that assume that there are not other UAVs, other planning agents at the same time. And then there are other algorithms that rely on centralized and or off-board planning. So if we really want to push the boundaries of the potential applications for UAVs, we need to relax these three assumptions. But first of all, let's start by understanding what trajectory planning actually entails. So trajectory planning entails the generation of trajectories that on one hand are dynamically feasible and on the other hand are collision-free. We want to do this on board, in real time, and in a world that is discovered as the engine flies. As an example, here you have some videos from my master's work where I developed this algorithm called FASTER that was able to perform obstacle avoidance in static unknown worlds. Here you have two videos of two simulations, and here you have some hardware experiments. The thing is that we would like now to do this in an environment that contains dynamic obstacles and also other planning agents. And when there are other agents present, we want to do this in a decentralized and asynchronous way. In other words, we would like to fly in an environment that looks like this, where we have a planning agent, for example this one, that needs to fly to a different part of the world while avoiding static obstacles, dynamic obstacles, and also other planning agents. And this leads me to the problem statement of this thesis, which is real-time trajectory planning for UAVs in multi-agent and dynamic environments. So there are four challenges to this, and all of them can be visualized in this picture. In this picture, you have an agent, a UAV, that is planning trajectories while avoiding these three dynamic obstacles. So the first challenge we need to overcome is how to encode the trajectory in the constraints. The idea is that we will impose collision avoidance constraints, and we need to answer the question of what representation we are going to use of this trajectory in the constraints. Then we need to take into account the fact that there are other dynamic obstacles and other agents planning at the same time, and we need to ensure safety in these kinds of environments. Then we need to take into account that we have an onboard sensor that has a limited field of view, which means that we only gain information about the obstacles when they actually enter the field of view of the camera. And finally, we are in a dynamic world which demands very high replanning rates, which are actually pretty hard or pretty difficult to achieve in a computational constrained platform like this one. So these four challenges lead me to the four contributions of this thesis. We answer the question of how to encode the trajectory in the constraints by developing a novel polynomial basis called the MINVO basis that is able to find the tightest possible simplex of a given interval of a polynomial graph. Then we are able to ensure safety in an environment that contains dynamic obstacles or other agents by developing this algorithm called MATE. After that, we will include a perception-aware term to take into account the limited field of view of the camera. And finally, we are able to speed up quite a lot the computation time by developing a learning-based framework. So let me start with the first contribution. In this contribution, we want to answer a question of how to encode the trajectory in the constraints. The idea is that a common constraint in path planning is that we want the trajectory to be collision-free. Or in other words, we want the trajectory to be completely contained inside free space. So there are several ways to this. One possible way will be to use discretization, where the idea is that we take many points along the trajectory and then we impose as many constraints as discretization points. So this has two disadvantages. On one hand, this is not safe, and the reason why this is not safe is because we don't have any guarantees of what happens between two discretization points. And then on the other hand, we can actually get very high computation times due to the high number of constraints that we need to impose. Other option would be to leverage the convex hull property of the Bernstein or B-Spline basis, where the idea is that instead of imposing constraints on points along the trajectory, we now impose constraints on the control points of every interval of the trajectory. So this is clearly safe, and the reason why this is safe is because the convex hull property says that every interval of the trajectory will be completely contained within the convex hull of its control points, but on the other hand, this is conservative. And the reason why this is conservative is because we are using an outer approximation, an outer polyhedral approximation of the interval that that does not tightly enclose the given interval of the trajectory. So then the question I tried to answer here was whether or not there exists a polynomial basis, and by polynomial basis I mean a non-negative set of polynomials that form a partition of unity that is able to generate the tightest possible enclosure of a given interval of a polynomial curve. And this is what I call here the MINVO basis. So again, the idea of the MINVO basis is that we are given this polynomial curve in red, and we want to find the tightest possible simplex in green that completely encloses this polynomial curve. And this is problem 1 here. So of course, this problem 1, the solution for this problem 1 will depend on one hand on the given curve, and then on the other hand on the degree of this curve n. We could also be interested in the opposite problem, where we are given the simplex, and we want to find the polynomial curve that has the largest convex hull and that is completely enclosed within this simplex. And this is this problem 2 over here, which in this case, of course, will depend on the given simplex and also on its dimension n. So it turns out that both problem 1 and 2 can be solved if we are able to solve problem 3. The interesting thing is that problem 3 depends only on n. In other words, if we are able to solve problem 3 for a specific n, let's say n equals 3, then we have the solution for problem 1 for all the curves whose degree is 3, and then we also have the solution for problem 2 for all the simplexes whose dimension is 3. The tricky part here is that in problem 3, we are maximizing the determinant of a non-symmetric matrix, and therefore this is a non-convex problem. And moreover, we also have this infinite constraint over here. However, we can leverage some of the squares programming, moment relaxations, and branch and bound, and we were able to find the solutions shown here. So we were able to prove numerical global optimality from n equals 1 to n equals 3, numerical local optimality for n equals 4, and then we were able to obtain high-quality feasible solutions for any degree n. So the way this looks for n equals 3, for example, from the point of view of problem 1, here we show that the simplex obtained by the MINVO basis is 2.4 and 255 times smaller than the simplexes obtained by these two other bases. From the point of view of problem 2, where the simplex is given, we are able to obtain a polynomial curve in red whose convex hull is 2.4 and 255 times larger than the convex hulls of the curves obtained by these two other bases. So then, the way this works is as follows. You are given the polynomial curve, and you have to do a simple matrix multiplication to obtain this enclosing simplex in green. And similarly, from the point of view of problem 2, you are given the simplex, and you do a matrix multiplication to obtain the polynomial curve that has the largest convex hull. And you can apply this to any random 3D polynomial curve, like all these ones. For example, you just take the coefficients, you do again another matrix multiplication, and you obtain these simplexes over here. And also, from the point of view of problem 2, you are given the simplex, you do another matrix multiplication, and you obtain these curves whose convex hulls are in blue. And actually, then you can obtain a tighter polyhedral approximations by taking the curve, splitting it into several intervals, then you compute the MINVO simplex for each one of these intervals, and then you compute the convex hull of all of them. And these are the outer polyhedral representations that you obtain. So there are quite a lot of applications for the MINVO basis. The one we were interested in was path planning, where the idea is that now we can impose in a less conservative way collision avoidance constraints both in position space, this third column, and also in velocity space. But then other potential applications for this MINVO basis is, for example, reachability analysis of polynomial systems to find the roots of some polynomials, and also for computer-aided design, like, for example, to perform rendering, to obtain intersections, or to perform rasterization. And related to this last point, we actually developed quite a lot of extensions of this MINVO basis, where we applied it to surfaces, to some rational curves as well, so not just polynomial curves, but also some rational curves. We also developed some beautiful geometric interpretations of the problem that the MINVO basis is trying to solve. And then we compared it with another state-of-the-art method called sleeves that is extensively used in CAD. And specifically in these comparisons, we were able to prove that the MINVO enclosure can be obtained 20 times faster. And if you fix the number of vertices, then the MINVO basis is able to achieve a smaller volume. So I'm not going to go into all the details of all these extensions, but I'm more than happy to take any questions that you may have. And with that, I finish this first contribution, whose outcome has been this journal paper published in the CAD journal. Okay, so now that we have a less conservative way to impose collision avoidance constraints, now the question is what happens if we have dynamic obstacles or other agents. And let's start first talking about how to encode dynamic obstacles in the optimization. So there are several ways to this. One possible way will be to impose point-wise constraints between the trajectory you are optimizing and the trajectory that the obstacles are executing. Of course, this can very easily make the problem intractable due to the high number of collision avoidance constraints. Other option would be to rely on nice solutions, like for example, you take all the space that an obstacle is going to use in a given planning horizon and you classify it as occupied. But of course, this can very easily lead to infeasibility. So then the proposed solution is as follows. The idea is that we take the trajectory we are optimizing, which is this one, and the trajectories from the obstacles, and we compute an outer polyhedral representation of every interval of each one of these trajectories. So to compute this outer polyhedral representation, if the trajectory is a spline, we can do this very easily by just using the MINVO basis, or more in general, if the trajectory is a function of time, we can always discretize it, compute the convex hull of the Minkowski sum, and then inflate it with the error induced by the discretization. Either way, we obtain an outer polyhedral representation of every interval of all these trajectories, and then we simply need to enforce linear separability between every pair of polyhedra. For example, between this polyhedron and this polyhedron, we obtain this plane that separates both of them. This is a 2D representation, but our algorithm, of course, works in 3D, where the idea is the same one. We are optimizing this trajectory, and we have the trajectory of the obstacle, for example, this one. So what we do is we split both trajectory into several intervals, in this case 7 intervals, and then for every interval we impose linear separability via planes that separates the outer polyhedral representation of the first interval, in this case of the trajectory of the obstacle, and the outer polyhedral representation of the first interval of the trajectory we are optimizing. And we do that for all the intervals. So then the way the optimization problem looks is as follows. We want to maximize the smoothness of the trajectory. We want to impose these initial and final conditions. We have the collision avoidance constraints, and we also have these dynamic limits. The problem here is that we are actually including the planes as decision variables. So this n over here and this d are decision variables, which make the problem a non-convex problem, for which an initial guess is imperative. To obtain this initial guess, we develop an algorithm called octopus search, that it is a search-based algorithm that is able to operate directly with the control points of the intervals. In other words, by construction, the output of this algorithm will be a trajectory that will satisfy, on one hand, the initial and final conditions, and also the smoothness constraint. And then this algorithm is able to handle dynamic obstacles by using the MINVO basis and returning the planes that separate every pair of polyhedra. So this is an algorithm we have tested extensively in simulation. In this case, you have a single agent simulation with 150 box-like dynamic obstacles. And now we increase the complexity of the simulation, including heterogeneous dynamic obstacles. And everything here is running completely in real time, in this case in my laptop. Okay, so far we have talked about how to avoid dynamic obstacles. Now the question is what happens if there are other agents present in the environment. So there are two challenges that appear here, and both of them are related to the fact that we want this algorithm to be decentralized and asynchronous. By decentralized, I mean that the optimization problem is solved independently by every agent, and by asynchronous, I mean that we don't want to impose any ad hoc dependency between the replanning status of different agents. So this is something that has been studied quite a lot in the literature, and here in this table you have a summary of some related works. And the idea is that we want to create an algorithm called MATHER that is both decentralized and also asynchronous. The reason why we want this algorithm to be decentralized is because it offers a better scalability with respect to a number of agents, and it also has an increased robustness. We also want this algorithm to be asynchronous because on one hand, it has a better performance across all the agents, and then it also has an increased robustness. But of course, the natural question is how to ensure safety while being completely decentralized and asynchronous. And the proposed solution is as follows. The idea is that we divide the replanning step into 3 steps. Optimization step, which is this one, check step, which is this blue one, and then recheck step, this red one. And here you have a plot of 2 agents, agent A and agent B, where the x-axis is time. So the idea is that agent A, for example, will start the optimization at this point, and at this moment, agent A will take the trajectory that agent B is executing as a constraint in the optimization. In other words, this blue trajectory over here is the trajectory that agent B is executing here. And agent A will start the optimization. However, as this is a completely decentralized and asynchronous algorithm, agent B will start the optimization, for example here, and then it's able to finish it before agent A finishes the optimization at this point. So that means that when agent A finishes the optimization here, the optimal trajectory that agent A has found may actually collide with the trajectory that agent B is executing here. That's the reason why agent A needs to run this check step, where the goal is to make sure that the optimal trajectory does not collide with the trajectory that agent B is executing. So if this check is not satisfied, then agent A will keep executing the trajectory it had at the beginning of the optimization. But if this check is satisfied, then agent A needs to move to the recheck step. The idea of the recheck step is that agent A needs to ensure that there are no trajectories published during this check phase. And this is actually implemented as a fast Boolean comparison. So if both the check and the recheck are satisfied, then agent A will commit to the optimal trajectory found at this point. Okay, so this is something we have tested extensively against many other different state-of-the-art algorithms. And here we compare, on one hand, or we classify them according to whether or not they are decentralized, they have replanning, they are asynchronous, and whether or not they rely on discretization. And then in the second part of the table, we compare the computation time, execution time, and total time of these algorithms, the total flight distance, and also we classify them according to whether or not they are safe. So the main 2 takeaways of this table are these 2 ones over here. So Mader was the only algorithm that is decentralized, has replanning, and is asynchronous, and is able to either equal or even outperform some of the other algorithms that are either centralized or even synchronous. And here you have some examples of the simulations performed. In this case, we have a circle environment with 16 agents. Now we do this simulation, but with 32 agents. And now we move to a sphere configuration. First with 16 agents. And now with 32. And this is an algorithm that we have actually also deployed on real hardware. And here you have 6 agents planning trajectories and performing obstacle avoidance in a completely decentralized and asynchronous way. Here we were able to achieve maximum velocities up to 5 meters per second. And I want to give credit here to Kota Kondo, who is a lab mate and that has done quite a lot of work with these hardware experiments. Okay, and with that, I finish this second contribution, whose outcome has been this TRO paper over here. Now the thing is that in this second contribution, we assumed that we had access to the future trajectories of the obstacles. But that's not the case in the real world, where we have a dynamic obstacle that is following a trajectory that is completely unknown to the agent. In other words, we need to start thinking about how we can take into account the limited field of view when planning these trajectories, because the field of view is the only way by which we will detect the obstacle. So again, the goal here is to avoid unknown dynamic obstacles that are actually detected by the onboard camera. In other words, we need to leverage the planned trajectory to make it easier to detect these obstacles. So there are several ways to do this. One possible way will be to not be perception aware, which of course leads to very poor results, and then other possible way will be to be perception aware but with additional hardware. However, this second approach requires mounting a gimbal, for example, on board, which is usually undesirable in very small UAVs. So then the third approach is perception aware planning. And within this approach, we have two options. We can decouple translation and yaw, where the idea is that, for example, you first optimize translation, then you fix it, and then you optimize the yaw trajectory. So they have very low computation times, but it's very conservative. And the reason why this is conservative is because we are not allowing the optimizer to modify both translation and yaw to decrease the cost of the objective function. Other option would be to jointly optimize translation and yaw, which of course is less conservative but comes at the expense of large computation times. Of course, if you, for example, don't perform obstacle avoidance, you can actually reduce the computation times, but as soon as you want to perform obstacle avoidance, and especially with dynamic obstacles, this computation time usually explodes. So then the research gap is how can we ensure computational tractability while jointly optimizing both translation and yaw. So there are two reasons why this problem can become computationally intractable. The first one is because of the way we are imposing collision avoidance constraints with dynamic obstacles. But the good news here is that we can actually leverage MINVO, which is the algorithm I have explained before, to be able to perform this obstacle avoidance with dynamic obstacles. Then, the second reason why this problem can become computationally intractable is because of the way we are imposing the underactuated constraint that couples acceleration and rotation. So, in an underactuated UAV like this one, we have that this constraint over here needs to be satisfied at all times. This constraint says that the last column of the rotation matrix needs to be equal to the normalized relative acceleration. The thing is that if we impose this constraint explicitly in the optimization problem, on one hand it leads to more decision variables, and on the other hand it leads to two non-convex constraints. So this constraint itself and also the constraint of this rotation matrix being inesotary. So then what we propose is to impose this constraint implicitly, not explicitly, by choosing a specific parameterization of the rotation. And in this case, we use the inverse image of the Hopf vibration. So a Hopf map is a map that takes a unit quaternion in S3 and maps it to the rotation that this quaternion produces in the vector 0, 0, 1. So what we do is we use the inverse image of this map to be able to define the rotation of the body frame as a composition of these two quaternions. The first quaternion will align this B3 vector with the normalized relative acceleration, and the second quaternion will perform a rotation around this normalized relative acceleration with an angle psi. The thing is that if you compute the rotation matrix associated with this quaternion and you plug that value into this equation, then this equation is satisfied at all times. In other words, we can drop this constraint because it will be satisfied by construction. Of course, the natural question to ask is this the only possible parameterization that you can use? And the answer is no. There are many different definitions of the differential flatness map that takes an acceleration vector and a yaw angle and map them to the rotation matrix in inesotary. The thing is that this map will at least have one singularity, and this is due to this famous hedgehog or hairy ball theorem. The problem here is that by changing or by using different definitions, we can actually create more or fewer singularities, and we can also change the location where they appear. For example, if we use this definition over here, we end up with two singularities that are at these 2 points over here, corresponding to the place where the drone is pitched down 90 degrees and when it is pitched up 90 degrees. We can move these singularities from pitch to roll by using this second definition, but the cool thing is that what the Hopf vibration does is it takes these two singularities and it places them at the same point, which corresponds to the upside down configuration, which is actually the point that maximizes the great circle distance with respect to the hover condition. And this is why we decide to use the Hopf vibration map to perform obstacle avoidance. So in terms of the architecture, we have the incoming point cloud over here, and then we have all these blocks whose task is to be able to predict the future trajectories of the obstacles. Here we rely on a simple algorithm consisting of first performing clustering and then running the Hungarian algorithm, but we could also use other more state-of-the-art algorithms like all these ones. Once we have the predicted trajectories of the obstacles, we run the octopus search algorithm, which is the algorithm I have explained before, to obtain the position guess. This position guess will be used in a graph search to obtain the yaw guess, and then the position guess and the yaw guess will be used in the optimization. So the optimization takes this form over here. We want to maximize the smoothness of the trajectory while maximizing at the same time the presence of an obstacle in the field of view and minimizing its projected velocity to minimize the blur in the image. We also have initial and final conditions, these collision avoidance constraints, and then these dynamic limits. So in these simulations, we focus first on a simulation where there is only one obstacle, and the idea is that we have an obstacle that is moving around and the UAV needs to go from one point to another while passing through the area where this obstacle is moving. And in this first part, we compare the frequency of the presence of this obstacle in the field of view. So here you have in all these plots the image plane, and this first plot is an approach that is not perception aware. This second one is an approach that is perception aware but decouples translation and yaw. And this third approach is our approach PANTHER, which jointly optimizes both translation and yaw. And in red, you have the field of view. So as you can see, PANTHER is able to keep the obstacle in the field of view much more frequently than these two other approaches. And then we look at the number of continuous detections that we are able to achieve. In other words, the number of consecutive frames in which the obstacle is kept in the field of view. As you can see, PANTHER, which is this box plot over here, is able to achieve longer continuous detections compared to these other approaches. We now move to a simulation where we have multiple obstacles, and here the task is to fly from this starting location to this goal location while avoiding these 5 dynamic obstacles. So we perform first a simulation where the obstacles are moving slowly, and then we also perform another simulation where the obstacles are moving faster. And we compare all the algorithms, both in terms of the number of collisions and in terms of the success rate. And here, the algorithms we compare are these 5 ones. In blue, you have approaches that are not perception aware. In orange, you have approaches that are perception aware but decouple translation and yaw. In yellow, you have approaches that perform a sweep in the yaw angle back and forth. And then in purple, you have an approach that makes yaw such that the UAV points to the direction of travel. And in green, you have PANTHER, which is our algorithm. So as you can see, PANTHER is able to achieve fewer collisions and a much higher success rate, while achieving a very similar flight time and distance. If we move now to the hardware results, so I'm going to show you a video in the next slide, but the idea is that in all these hardware experiments, all the computation will run completely on board the agent. And then the agent does not have any prior knowledge of the trajectories or even the shape of these obstacles over here. And the only sensors that we use are a depth camera, which is pointing forward, a monocular camera that is pointing downwards, and then an IMU. So these are the 9 experiments that we performed where we were able to achieve a maximum velocity of 5.8 meters per second and a maximum relative velocity of 6.3. And these are the experiments. So in the first 2 experiments, we used one obstacle. In the third experiment, we use 2 obstacles, and then in the rest of the experiments, we use 3 obstacles. And in all these videos, you have here the onboard forward-facing camera, the onboard downward-facing camera, and then the field of view of the camera over here. And again, in all these videos, the agent does not have a prior knowledge of the trajectories or shape of these obstacles, and everything is running on board and in real time. And with that, I finish this third contribution, whose outcome has been this journal paper over here. Now the question is the following one. So Panther worked really well, but its main two disadvantages were the fact that the solutions were a little bit conservative, and then the computation times were between 70 and 100 milliseconds. And with this fourth contribution, I answer the question of whether or not it's possible to create perception-aware trajectories, which are similar to the one we were creating here, but that are on one hand less conservative, and on the other hand, we are able to obtain them with much less computation time. So again, the main two disadvantages of Panther were that the solutions were a little bit conservative, and then the computation time was between 70 and 100 milliseconds. In other words, if we plot the results obtained by Panther in this plot where we have cost versus replanning time, Panther operates in this area over here. So let's start first by thinking about this first point over here. Is it possible to create solutions that are less conservative? And the answer is yes, and it's actually pretty easy. For example, we can include in the optimization the time allocation and the planes that were fixed in the Panther optimization, but that now are actually decision variables in this Panther star optimization, where Panther star is this less conservative algorithm. We actually also run 10 optimizations with 10 different initial guesses. The idea is that Panther was run only once with one initial guess, and here we create many initial guesses and we run one optimization for each one of these initial guesses. Of course, these less conservative solutions come at the expense of computation time. So we go from this part of the plot to this other part where we can see that we have been able to decrease the cost, but at the expense of replanning time. Here we are talking of replanning times of around 1 second. So then the question is whether or not it's possible to operate in this area, where we have a cost very similar to Panther star, but with a replanning time much smaller. And this is what we call Deep-PANTHER. So the proposed solution to attempt this is based on imitation learning. Here, Panther star will be the expert, which is this green dots over here, and then Deep-PANTHER, which is the neural network, will be the student. And this is something that we train using the dataset aggregation algorithm. Okay, so first of all, let's define the observation and the action. So the observation, which will be the input for both the expert policy and the student policy, will consist of the state of the UAV, defined by its velocity and its acceleration, the goal for the UAV, then the predicted trajectory of the obstacle, defined by its control points, and then the size of the obstacles. And this leads to an observation that has 43 elements. In terms of the action, which will be the output of, again, both the expert and student trajectories, we are doing trajectory planning, which means that the output will be a trajectory. In this case, we parameterize this trajectory in the action by using the control points. And the thing is that we actually don't need to include the first 3 position control points and the last 2 position control points, because they are determined directly by the initial and the final conditions. In other words, we only need to include these blue intermediate control points. So that means that the action will be as follows. Will consist of the intermediate control points, these ones, and then the total time of the trajectory. And then the idea is that we want to plan more than one trajectory, and that's why we have this n over here. So by choosing this action, the initial and final conditions will be automatically satisfied, and then the smoothness will also be satisfied by construction due to the fact that we are using the control points. And then this leads to an action whose size is 13 times n, where n is the number of trajectories that we generate. The question now is how we can capture the multimodality of the expert. The idea is that, for example, if you are in this situation over here and you want to plan a trajectory from this starting location to this goal location, and you run this optimization with 10 different initial guesses, in other words, you run 10 different optimizations, all of them converge to the same locally optimal solution, which is this one. If you move the goal a little bit to the left, like in this situation, then you end up with 2 locally optimal solutions. And then you can actually, according to the place where you put the goal, obtain 3, 4, or more locally optimal solutions. So then the question is how we can capture this multimodality with a neural network whose output has fixed size. So the way we propose to this is as follows. We take the observation and then we pass it through the student to obtain these red trajectories, and then through the expert, which is the optimization-based framework, to obtain these green trajectories over here. Once we have the red and the green trajectories, we compute the cost matrices, both in time space and in position space, and then we obtain from them this assignment matrix that will be the one in charge of penalizing only the pairs that have been assigned to each other. For example, in this case, we are penalizing the first trajectory of the expert with the second trajectory of the student, with this one over here. Now the question here is how to do this, how to go from a cost matrix to this assignment matrix. So to summarize what I have just said, we have the observation, we pass it through the student to obtain these red trajectories, and through the expert to obtain these green trajectories. We then compute this cost matrix, and then the question is how we can obtain this assignment matrix from this cost matrix, which is the one that will be used in the cost. So a very popular approach to this is called the winner-takes-all approach, which has two conventions, the row convention and the column convention. In the row convention, what we do is we assign each expert trajectory to the closest student trajectory. In other words, we take each one of these green trajectories and we assign them to the closest red trajectory. And it leads to an assignment matrix A whose rows will sum up to 1. You can relax this approach, and instead of forcing A to be a binary matrix, you can include this epsilon to include or to add soft weights between all the trajectories of the student and all the trajectories of the expert. And then we have the other convention, the column convention, where each student trajectory will be assigned to the closest expert trajectory. In other words, each one of these red trajectories will be assigned to the closest green trajectory. And in this approach, you end up with an assignment matrix whose columns will sum up to 1. The problem, of course, you also have the relaxed version of this approach where you include this epsilon and to add the soft weights between all the trajectories of the student and all the trajectories of the expert. But the problem with these two approaches are these two ones. On one hand, the row approach may run into equilibrium issues where the idea is that the student predicts a trajectory that ends up lying between several expert trajectories, which can actually be catastrophic in an obstacle avoidance scenario. In the other approach, in the column approach, we may run into mode collapse issues where essentially many or all of the trajectories of the student end up predicting the same trajectory of the expert. Or in other words, there are some trajectories of the expert that are never predicted by the student. So to solve these issues, we propose to use this other approach, where what we do is that for each expert trajectory, we assign it to a different student trajectory while minimizing at the same time the assignment cost. In other words, what we do is we solve the Hungarian algorithm. And this leads to an assignment matrix A, which is this one over here, whose rows will sum up to 1, and that will have n sub e columns that will sum up to 1, where n sub e is the number of trajectories produced by the expert. Okay, so that allows us to obtain the position trajectory, which is, let's say, for example, this one over here. Another question is how we can obtain the yaw trajectory. The thing is that if I give you the position trajectory and the time allocation, then you already know 2 degrees of freedom of the rotation due to the underactuated constraint of a UAV. But now we are interested in finding the yaw trajectory, which is the 3rd degree of freedom, and specifically we want to find the yaw trajectory that maximizes the presence of a given feature, static or dynamic, in the field of view. So it turns out that there is a closed form solution to do this, to go from the position trajectory to the optimal yaw trajectory that maximizes the presence of a given feature in the field of view, which is this red trajectory over here. And this solution actually comes from solving the KKT equations associated with an optimization problem. So that means that at testing time, what we do is as follows. We take the observation, we pass it through the student to obtain the intermediate control points and the total time of the trajectories. Then we impose the initial and final conditions to obtain all the position control points and all the times of the trajectories. With these position trajectories, we then use this closed form solution to obtain the yaw control points, and then we rank all of them according to the cost and to the constraint satisfaction to be able to obtain the best position and yaw trajectories. Okay, so let's move now to the results. In this case, you have the same plot I have shown you before, where you have cost versus replanning time, which consists of, or which are the results of this simulation experiment, where you have the UAV over here that needs to plan a trajectory to go to each one of these 64 goals. So as I said before, here you have the results that Panther obtains, and then the expert, Panther Star, is able to obtain results over here, where again we have been able to decrease the cost, but at the expense of computation time. The cool thing is that Deep-PANTHER is able to obtain results here, where we can see that we have been able to obtain a very similar cost compared to the one obtained by Panther Star, but then we are achieving a reduction of 1 order of magnitude in computation time with respect to Panther, and of 2 orders of magnitude in computation time with respect to Panther Star. We also study how the choice of the assignment affects the solution, and in this table we compare how similar the trajectories that the student produces are to the trajectories of the expert. So in the columns here you have the value of epsilon, which is essentially a way to quantify the relaxation that we are performing. In other words, epsilon equals 0 means that the assignment matrix will be a binary matrix, and then epsilon greater than 0 represents a higher degree of relaxation. And here in the rows, you have ratios where we compare the mean squared error of a given policy using the winner takes all algorithm, and then the mean squared error obtained by our approach. In other words, every number of this table that is greater than 1 means that our approach is able to generate trajectories that are closer to the expert, which, as you can see, happens in all these epsilon values tested. And then we compare the number of collision-free trajectories. So for each one of these 64 goals, we plot them in this matrix. So every cell of this matrix represents a different goal in this 3D environment. So a square is green if we are able to obtain at least 1 collision-free trajectory, and a square will be red if the algorithm has not been able to obtain at least 1 collision-free trajectory. So as you can see, our algorithm, which is this one, is able to obtain at least 1 collision-free trajectory for all the 64 goals tested. Okay, so let's see now how the expert demonstrations look like, and let's start first with a static environment. So these are the expert demonstrations that we collect. In this case, as you can see, we randomly deploy the obstacle in the environment, and then we also randomly choose the goal. So this is again for training, but then this is what happens for testing. Whereas you can see for all the 64 goals, our algorithm is able to produce always at least 1 collision-free trajectory. If we move now to a dynamic environment, these are the demonstrations that we collect from the expert. In this case, the obstacle is following a trefoil knot trajectory. And then we test it and deploy it in an environment where the obstacle is also following a trefoil knot trajectory. As you can see, the performance is pretty good, both in terms of how it's able to avoid the obstacle, but also in terms of how it's able to keep this obstacle in the field of view. Of course, the natural question here is how well this generalizes. So as I have said in the video before, we had trained the policy in an environment where the obstacle was following a trefoil knot trajectory, and when we deployed that trained policy in the same environment where the obstacle was following the same trajectory. Of course, the question is what happens if the obstacle is following different trajectories. And here we test the train policy with these other 4 different trajectories, when the obstacle is static, or when the obstacle is following a square, an 8, or an epitrochoid. And we look at the amount of replanning steps that are able to generate at least 1 collision-free trajectory. And these are the results. So in this first video over here, we deploy the train policy in an environment where the obstacle is following the same trajectory as the one used for training. And then in these other 4 videos, we deploy the train policy in an environment where the obstacle is following a different trajectory. So in the first case, we are able to obtain this value over here. That means that 100% of the replanning steps are able to generate at least 1 collision-free trajectory. The interesting thing is that actually for all the other trajectories, we are also able to obtain 100% of success rate. In other words, 100% of the replanning step we're able to generate at least one collision-free trajectory, which means that Deep-PANTHER is able to generalize pretty well to other trajectories that have not been seen in training. And with that, I finish this fourth contribution, whose outcome has been this RAL paper that we are actually about to submit right now. Okay, so here you have the publications of this PhD. So in the first table, you have the main publications during the PhD, and then in this other table, you have also other publications I have worked on, in other projects throughout the PhD as well. So in blue, you have a conference paper, and then in orange, you have a journal paper. And with that, I would like to thank you so much for your attention, and now I am happy to take any questions that you may have. Thank you.